Wait, hold the music. Imagine you're a student. The class is now on Chapter 8, and you haven't yet studied Chapters 1 through 7. You'd have some pretty basic questions, huh? But imagine you're also quite the curious student. You'd have quite a few questions. This describes our co-host for these next 2 episodes on the nature of water, a hilarious, endearing, and willing victim during a recent trip to visit her son, my mom. A student of life, your guardian, here to make sure the concepts presented to you, the listener, are absolutely clear. Okay.
Ice has water on the top of it, and that's why you can do the ice skating. That's really weird. You would think they were skating on ice, but they aren't. So why do we say he's skating on ice when actually he's skating on water?
That's a good point.
It is.
Can you introduce us?
Welcome to the Big Picture Podcast. My name is Marjorie Suhaki, and I am here as your co-host as we explore this chapter on water.
Mom, thank you so much for joining us here.
I'm glad to do this, son.
Quite the honor. Welcome to the Do Review section for this chapter on how water behaves. In this chapter, we start with water in the solid phase, then we move to the liquid phase, and then to the gaseous phase. We'll be exploring the multitude of amazing properties for the water molecule, very dear to all of our hearts. So here we are in the first section. Water molecules form an open crystalline structure in ice.
What does it look like at the level of molecules?
Well, recall earlier we've talked about water being analogous to a bunch of marbles in a bag. The marbles can tumble over one another, and you can pour the marbles out of the bag, kind of like a fluid. Let me say exactly like a fluid. Consider the water molecules like tiny, tiny, tiny little marbles. And when you have the water within a cup and you pour the water out, envision all those tiny, tiny, tiny water molecules tumbling over one another as they flow out of the cup. So that's perhaps the best place to begin, of thinking of liquid water as a bunch of marbles tumbling over one another.
They like tumbling.
Yeah.
It's their nature to tumble.
But they also like each other, because remember we talked about the dipole-dipole attractions?
Oh, yeah. So actually they're playing with each other, speaking as your mother.
That's a good way to put it.
Okay.
For each water molecule, one side slightly negative, the other side slightly positive. Each water molecule has a dipole, which makes them slightly sticky. So two water molecules are attracted to each other by the dipole-dipole attraction. So what we're going to do now is we're going to lower the temperature of this water.
I bet that means they won't run quite so fast.
As you remove the energy from the system, indeed, you will find the molecules start to slow down. They'll slow down to the point where the molecules can no longer tumble over one another quite so well, and they become eventually immobile.
Ice.
That's what you have in a solid phase
of water.
The water molecules are all found in fixed positions.
Wow. So while they are full of these molecules that have a tendency to run and
tumble over
one another, what's required in order for that to happen is a certain level of temperature, heat.
Heat. And if you remove that heat, they slow down to the point that they become fixed in their positions.
They fall asleep.
Well, not really, because it's quite interesting. Think of it this way. They're no longer tumbling around one another. But that's not to say they're not moving.
Well, how are they moving?
Bzzz.
Like moving in place?
Yes, they're vibrating in place.
Ah, okay.
So once you get them all frozen in a solid phase, is it possible to get it any colder?
Actually, I would say no.
But you see, what's the difference between ice at minus 10 degrees and ice at minus 50 degrees?
Is there any difference?
Very much so.
Why?
Which has more energy?
Oh, the ones on the ones with
higher temperature, which is minus 10 degrees.
Yes.
So would you believe...
so wait a minute. They vibrate more slowly is what you're saying.
At lower temperatures.
At lower temperatures.
Yeah.
And can you get to a rock bottom temperature where they don't vibrate at all?
Well, that would be absolute zero.
Yes. Can they do that?
No, it's a theoretical point.
Really?
You can't extract all that energy. It takes an infinite amount of energy to extract that.
Kidding.
We talked about that. At absolute zero, only then do you get rid of the vibrational motion.
I think that's amazing.
Yeah. So water...
Wait a minute.
What?
Does that mean they're dead? Or can they be resuscitated with heat?
Nah, I think if you added the heat, they would start vibrating
Aha.
again. Okay.
Okay.
So they're not tumbling over one another. They're stuck. But in their stuck positions, they are still vibrating.
Yeah.
Now, here's the interesting part in terms of how they are fixed relative to one another.
Yeah, that's interesting.
Recall water has a bent shape to it.
Yes, I remember.
Yeah.
Weird.
So we were going over this earlier. The water molecule has a bent shape, and that comes from the tetrahedral nature of its electron geometry. And from that tetrahedron nature, you'll find each water molecule extends itself in 4 different directions. And just add it all up, you end up with this crystalline structure that's an open crystalline structure, like a jungle gym maybe on a playground. You've got the kid can run through all the bars. What's in those bars is the empty space. And at the intersection of each bar, that's where you have your water molecule.
Okay.
The water molecules are stuck in place in this, what we call an open crystalline structure. And there's the space that's in between those water molecules. And as it forms this crystalline structure, it has this tendency to pucker up. It actually occupies more volume once it freezes.
Oh, it expands.
It expands.
Of course it does.
Significantly. And you know that if you take water in a jar and you close the jar and then you put it in your freezer.
Oh, yeah.
What happens to the jar? It cracks because the water is expanding.
I know.
So when water freezes, all those water molecules, they enter into this open crystalline structure that puckers out, occupying much more
volume,
more space.
I was imagining something.
What?
I was imagining when I was a kid, we used to play down in the marsh, and we used to go in these old houses that sometimes people lived in, and most of the time they didn't. And there was a jug of water on the table, and my friend and I said, "Oh, look, somebody's been here." Next time we came, there'd been a frost, and when we came, and there was glass all over the place, and the water was gone.
Glass jug?
Yes, it was a glass jug, and we knew that someone had come in while we were gone and broken that juggle of water.
The mystery has been finally solved.
Yes, I know it.
It did itself.
We had more time imagining who the robber was who came in to break that that jug of water.
Oh.
Yeah, so see, when you talk about water expanding when it gets colder, I instantly remember the Phantom Thief.
So there's an interesting question to ask.
What?
There's space in between those
What
water molecules.
What fills that space?
What fills that space? A, air. B, water vapor. C, nothing.
Nothing.
Absolutely nothing. That's correct. Good job.
I thought nature abhorred a vacuum.
Well, there it is. There's your vacuum.
Ah.
Yeah. We do mean open space, literally space. Like the Starship Enterprise could go whizzing through there.
Ooh.
If it were small enough.
If it were.
About
Why
ice.
doesn't it collapse on itself?
Why doesn't a building collapse on itself? There's the architecture, right?
Yeah.
You build the iron grids just so that it's self-supporting.
Yeah, that's right.
It's the architecture. It's because of the architecture that prevents
So
that
the
from happening.
architecture of the molecule itself is what keeps it from falling in on itself.
There's the architect of the molecule and then the architecture of all those molecules together.
Yes.
All those molecules together building a superstructure.
Yeah.
Which we call this open space crystalline structure
Oh,
of
how
ice.
interesting. And that makes it beautiful. Okay, what comes next?
Next, we're going to talk about the melting process.
Okay,
We're going to go from the solid phase now to the liquid phase.
is it any more than the fact that heat is applied?
Nope. That's all.
That's it?
Let's consider an ice cube in water,
All right.
in liquid water. So you have an ice cube submerged in liquid water.
Mm-hmm.
Now, in the ice cube, you find all those water molecules are stuck in their fixed positions.
Yes, that's right.
Outside the ice cube in the liquid water, they're all tumbling over one another. Or as
that's right.
you say, they're playing.
Yeah.
So what we want to look at here is what's happening at the interface
Yeah.
between the solid water and the liquid water.
Yeah.
And here's something people don't quite realize. Freezing and melting go on at the same time. It's a dynamic process. At the surface, you will find water molecules leaving the ice going into the liquid water. And at that surface, you will also have liquid water molecules that attach to the ice surface and get stuck.
Ah.
So you have a melting process
of
water
course.
molecules leaving the ice cube to the liquid, and you also have a freezing process of water molecules going from the liquid to the ice.
Yes.
Let's
of
look at it
course.
from the point of view of a water molecule that's a liquid, right?
Yes.
There you are, a water molecule playing around with your neighbors, tumbling
Yes.
over one another, having a good time.
Yeah.
Then suddenly you hit into this ice cube.
Yes.
You'll get stuck like a fly on flypaper.
Wait a minute. I thought an ice cube in water would melt, but
It does. It does both.
But
is
it
the point.
also, at the same time that in one respect it's melting, in another respect, as it loses, it also adds.
Yes. It's kind of like a revolving door at a department store.
Yeah.
You got people going out of the store, you got people going into the store, right? And when they're leaving the store, let's say that's water going from the solid to the liquid phase.
Yeah.
When they're entering the store through the revolving door, it's like from the liquid into the solid phase. So
Right.
the store represents the ice cube.
Yeah.
We have a rate at which water molecules are leaving, and we can have a rate at which water molecules are entering.
Oh.
And when you take ice and you throw it into water that is at 0 degrees Celsius,
Yes.
what's special about 0 degrees Celsius?
What is special about 0 degrees
At
Celsius?
0 degrees Celsius, the rate at which they leave the department store is equal to
Is
the rate
same as those coming in.
as they go in.
So it's a stasis.
That's it. Good word, meaning it doesn't change. Well, it's weird. On a molecular level, all sorts of stuff happening, but at 0 degrees, you will be able to have your ice cube indefinitely.
Yes.
There will be
Wow.
water molecules leaving that ice cube and coming back into the ice cube, back and forth, back and
Yes,
forth,
yes,
back and
yes.
forth. On a molecular level, it's really dynamic.
Wow.
The ice cube might be going through different water molecules, but you're still going to have the ice
yes.
cube
Yes. So it doesn't melt.
overall. Yeah, so it's a dynamic
Wait a minute. Let me
process.
ask you something else.
What?
Does it still cool the water?
The ice cube cools the water, but guess what?
What?
The liquid water warms up the ice cube. At 0 degrees Celsius, the two balance each other
Oh.
perfectly. Just take two water molecules in
Yes.
space.
Mm-hmm.
They're both dipoles, and so they're attracted to each other.
Mm-hmm.
As those water molecules come toward each other,
Mhm.
they accelerate toward one another.
Mhm.
And as soon as they collide,
Mhm.
they start vibrating and spinning around each other
Sure.
like crazy. So what
Yeah.
happens is you might have two water molecules that are out in space, not rotating or doing anything. And as they accelerate toward one another, they're picking up speed.
Oh, of course.
And once they do hit, they start vibrating like crazy. So
Yeah.
after they collide, suddenly they're moving like crazy. Remember we talked about temperature? The higher the temperature, the faster they're moving.
Mm-hmm.
Do you understand? Can you recognize that when they come together like that, suddenly the temperature's higher?
Sure.
Yeah, because they're moving faster, right? So we say it like this. When two water molecules come together, energy is released. So now say out in outer space you had two water molecules that were stuck together
Yes.
and you wanted to pull them apart.
Oh. Oh.
It's going to cost you energy, isn't it?
Yes.
Because they're stuck, like pulling two magnets apart.
Right.
Here you're trying to pull two water molecules apart. And they're going to, I don't want to leave my neighbor. We're attracted.
Right.
We've got both negative and positive charges, and we're fine.
We're perfect.
Leave us alone.
Yes.
If you wanted to pull them apart, you would have to put in energy and
You would have to put a heavy energy
Mm-hmm.
and force there to force them apart, whether they liked it or not.
so when the water molecules come together, energy is released.
Yes.
Once they're together, if you want to pull them apart, that requires energy. It's
That's right.
The opposite.
You got to put it back in.
Yeah. Now, that's important to understand, that whenever a liquid water molecule collides with the surface of the ice cube,
Yes.
it warms up.
Oh.
Because you're doing exactly that. You're forming
Oh, of course.
a bond, an interaction between that water molecule and this water molecule.
Yes.
So when the water goes from the liquid to the solid phase, energy is released, freezing is an energy-releasing process
Oh, my goodness.
because you're pulling water molecules together and energy is released. That's what freezing is.
Yeah.
Look at the reverse. If you wanted to pull those water molecules away from the crystalline structure, that's going to cost you energy. That's going to cool things down.
Mm-hmm.
So going from the solid phase to the liquid phase, that requires energy.
Mm-hmm.
So here's what happens. You have water and ice together at 0 degrees Celsius. Got that?
Mm-hmm.
And at that 0 degrees Celsius, you realize ice is being formed and at the same time ice is being deformed. And the amount of energy that's being released from the formation of ice is equal to the amount of energy you lose in the opposite direction.
Mm-hmm.
It balances out.
Mm-hmm.
Now what we're going to do is we're going to perturb the situation.
Oh.
We're going to start adding heat.
Yes.
An external source of heat, maybe a flame, maybe a little electric current. It starts warming up, and we get it to not 0 degrees, but maybe 5 degrees Celsius.
Uh-huh.
You're adding energy.
Yes. So it's going to
Guess-
start to break up.
Yeah. Guess which process you're going to favor? The one where you're breaking up, which requires the input of energy. Yeah? So you are favoring the leaving of water molecules from the ice cube into the liquid water.
Oh.
So you will find what happens to the ice cube.
Well, the ice cube melts.
You could do the reverse process. You could remove energy, lower the temperature from 0 degrees to minus 5 degrees, and you are going to favor liquid water molecules going into the ice cube, which releases energy that needs to be removed. Let's look at it this way. And this is counterintuitive, right?
Yeah.
Freezing is a warming process. Freezing is a warming process. Now explain that.
But it is a warming process.
Because you're forming bonds between water molecules. And as you form those bonds, heat is released.
Yes.
Yeah. And you know what? The only way to make it so that those water molecules stay together like that
Yeah.
is to make sure you remove that heat that was formed. And if you don't remove that heat that was formed, they're going to come right back out. And that's the function of a refrigerator.
Oh.
It removes that heat. Because if you don't, I'm sorry, it's just going to melt again.
Yeah.
So freezing, counterintuitive, I know, as it may sound, freezing is a warming process.
Isn't that amazing?
Now, let's flip it around.
Nobody would believe it.
Melting
Oh,
is a
cooling process.
cooling process. Absolutely. Explain that one now.
Oh, I can't. It's too much.
Oh, Mom, melting is a cooling process.
Melting is a cooling.
If melting, what's that mean? That means you have water molecules are together,
Yeah.
stuck in a solid phase, and you
No.
want them to pull apart
you
so they
want
can
them
go
to
to
start
liquid
playing
phase?
again.
You want to start playing again?
Yes.
Well, you're going to have to pull them apart first, and that's going to take energy. That's going to cost you energy to do that.
Yeah, where are you going to get
That's going
that
to cool
from?
things down.
Yes, it is. Yeah, because it's going to use the energy up in the process of melting.
That's it. Exactly. Bingo.
Okay.
Well said.
Suddenly it all makes sense.
Well, this podcast is one point of view. There's videos, there's the textbook, there's your instructor, there's your classmates, there's yourself.
I'm just glad I asked for this office hour because I would have had trouble all by myself, and I hope I can retain it so I do good on the test.
All right, so, here's the test. You
Oh,
ready?
no. I don't want to test. No.
Sorry.
What if I forget it all?
Well, the test is formative. It's there to help you learn.
Oh.
It's not to see what you've learned. It's there to help you learn it.
Okay, do we
You
have
ready?
to have the test? I'll be embarrassed in
we
front
got
of
it.
all your
Okay,
students.
so
Okay.
I'm going to paint a scenario for you.
All right.
Everyone, got your attention?
Yes.
Okay, here's the scenario. We're going to add a bunch of salt to the ice water.
No. Salt.
Salt dissolving in the liquid water.
That changes things.
Very much so. Now, you'll notice the salt doesn't go into the ice.
No.
Stir it up.
Goes into the water.
The sodium and chloride ions will be in the liquid water.
Yes.
First, before your exam question,
Yes.
it's important we understand what's happening at the molecular level when salt dissolves in water,
Yes.
right? And I like to think of it by analogy. It's like what happens when you pour a box full of heavy wooden marbles into a swimming pool. You still have the marbles, but you'll find they're all dispersed throughout the water. especially as you stir the water, as you mix it up, right?
All right.
Likewise, add salt to water, and all the sodium and chloride ions disperse throughout the water. You still have sodium ions and chloride ions. They're there and they occupy space, but you'll find they're all dispersed throughout the water, especially upon stirring the water.
Oh,
So that's the model to keep in mind when you think about salt dissolving in water. Got that? Ready?
all right.
Here's the test.
I don't want to test.
Think about what's happening at the interface. What have you done to the rate of molecules going from left to right versus right to
I
left?
think if you have added salt, you have messed up the process.
Let me ask you about the number of water molecules, liquid water molecules, that are now in contact with the ice cube.
Yes.
More or less.
Well, the salt has a melting.
No, forget that.
Okay.
Just think of the water molecules now mixed in with sodium ions and chloride ions.
Yes.
How many water molecules are now in contact with the surface of the ice, more or less? How about another analogy? Let's say you're holding 60 marbles in your hand.
Yes.
How many marbles are in contact with your hand?
60.
All right. Now, let's say you're holding 30 marbles in 30 rocks of the same size. How many marbles in contact with your hand?
30.
30, yeah. You see, the rocks occupy space.
Of course they do.
Yeah, and that means you have less marbles now in contact with your hand. The point is, when you have the sodium chloride in there, that makes it so there are now fewer water molecules in contact with the surface of the ice.
Because the sodium takes up space.
Yes. What's that do to the rate at which water molecules are able to go into the solid phase?
Oh.
Since you have fewer of them
Yes.
at the door, fewer molecules now are available to go into the department store, to go into the solid phase. There are fewer water molecules now going into the solid phase.
Then the solid phase is going to start diminishing.
The solid phase, however, has the same number of water molecules exiting the department
So
store.
it's going to get smaller.
And smaller and smaller and smaller.
Yeah.
You have upset the rate. All you've done is upset the rate at which water molecules go in.
Okay, my problem was trying to figure what difference it made that the salt came in. I was thinking if the salt dissolved, it didn't take up space anymore.
It
but
does.
actually, it does take up
Yes.
space. But once you say that, no, it continues to take up space, and it's just more in a dissolved state, but it still continues
there.
to take up space.
Those particles
Therefore,
are still there.
there are fewer to enter.
Yes.
But if the same amount is exiting,
Yes.
you're gonna.
Yes.
The ice is going to melt.
That's how salt
That was very
melts
difficult.
ice. But you did it.
Because it's really relatively simple.
Once you see the picture in your mind, all right, next up, an application of all we've been talking about is with the density of water. What do we mean by density?
What do we mean by density? Is how thick it is.
It's the mass per volume. Gold, you understand, is more dense than styrofoam.
Yes.
Yeah, so if you had a cubic meter of gold and a cubic meter of styrofoam,
A foot is a foot is a foot.
yeah,
Right.
so the
Okay.
volume
Okay.
is the same. You have the
Yes.
same volume of gold
Right.
as you have styrofoam,
That's right.
right? A cubic meter.
Yes. Yes.
So
But one will be more dense than the other.
the gold we know is more dense.
Yes.
So you put the two on a scale, which reads higher?
The gold would weigh
A
more.
lot more.
Yeah.
Yeah, so within that volume, you've got a lot more mass.
Yeah.
So we say it's more dense is because there's more mass
Yeah.
per volume,
Yeah.
right?
Yeah.
Even though this volume's same, the masses are going to be
I know.
different.
It's still a cubic
So
foot.
when we talk
But
about
you get a lot more gold in there than you do the other.
correct, because gold is more dense.
Right.
So here's the thing: the density of water changes relative to temperature.
Ah.
Yeah. Remember we talked about ice?
Why?
Well, here we go. Ice, when it forms, liquid water transforms into ice. It puckers up. Its volume increases
Yes.
because of the crystalline structure.
Yes.
Now, that means you have the same number of water molecules, but the volume is suddenly bigger.
Yes.
So that has the effect of making the density lower.
Yeah, it would.
You've got a lot of volume, but less mass in that volume.
Yeah. In other words, if you have a cubic foot of water, it will not make a cubic foot of ice. It might make
more than a cubic foot.
absolutely.
Right? Yeah. So the mass is the same, but the volume is greater, so the density is down.
Yes.
Is to say, ice cubes are less dense than water, which is why you talked about this before. What does an ice cube do when you throw it into water?
It floats.
It floats.
It's because it's not as dense.
It's not as dense.
Right.
That's it.
Buoyant. It's more
Excellent.
buoyant.
Yeah. So now we understand that solid water is less dense. And actually, it's significantly less dense than liquid water. But what we're going to do here is talk about the density of liquid water. It's an interesting profile.
Yeah.
Let's say you have water at 1 degree Celsius. That would be, 34 degrees Fahrenheit. And it's all liquid. You don't see any ice cubes in there at all. Pretty cold water. Here's the deal. At a microscopic level, interestingly enough, there are still tiny microcrystals in there. And those microcrystals of ice, they tend to increase the volume of the water because they're there.
Fattens it up.
Yeah, good way to think of it. How about warming it up to 2 degrees Celsius
You
now?
will have less of those crystals.
How about 3 degrees Celsius?
Well, pretty soon they're going to be gone.
Pretty soon they're going to be gone. You know what? They're gone at about 8 or 9 or 10 degrees Celsius.
Oh, really?
Yeah.
Okay.
So as you warm up that liquid water,
Yes.
the number of microcrystals you have in there decreases. What happens to the volume of the water itself? As you get fewer and fewer tiny micro ice cubes in there,
Then it would condense.
it gets more dense.
Yeah.
That's right. All right. So that's one trend to keep in mind. Got that? As you warm it up, you get fewer and fewer microcrystals, and so the density increases. Right. There's another trend that goes along with this. It's called the thermal expansion.
Okay.
As you warm something up, in fact, as you warm anything up, the atoms and molecules start moving faster and faster. They have a
Yeah.
tendency to expand.
Yeah, they run around again.
It's like the very reason why wires across telephone poles on a warm day, they'll sag more than during a cold day.
Straight during a cold day.
They're expanding.
Yeah.
So water as a material, when you add heat to it, because it makes the water molecules move faster,
Yes.
that makes the water want to expand.
Yes.
So we have two opposing trends here. The first trend is that the water is going to get more compact as you warm it up because you have fewer and fewer microcrystals. The second trend is as you warm it up, it tends to increase its volume because of the thermal expansion.
Yes.
Put those two together, and what we find is that water has its lowest volume at 4 degrees Celsius.
Oh, because after that it begins expanding.
The thermal expansion begins to become more important than the disappearing microcrystals.
Right.
So we find water is thus densest at 4 degrees Celsius.
Okay.
And that has huge consequences.
Tell me about it.
Ponds will always freeze from the top down. And
I know it doesn't because I've seen it.
Yeah, let's explain how so.
Well, first you get this thin film of ice, and it's on the top. It's
But
not on the bottom.
why is it on the top and not on the bottom? Let's start with the temperature of the air. It's in the wintertime.
Okay.
What's the temperature of the air?
It's going to be 4 degrees Celsius.
No, let's do a cold January day in New England, and let's say it's minus 10 degrees Celsius. It's really cold.
That's
out.
very cold.
It's very cold. So there you are, a bunch of water molecules on the surface of that pond.
You would think you'd want to huddle together.
It was a cold snap. Suddenly,
Yes.
you're liquid at this point, but suddenly the air around you is minus 10, 15 degrees
My
Celsius.
goodness, yes.
You start to cool down, don't you?
Yes, you do.
You do. So you're going to cool from, say, 10 degrees to 8 degrees to
Yes.
7 degrees. You're cooling down
Yes.
towards zero, right?
Yes.
Then you're 6 degrees, and then you're 4 degrees. And then before you get to zero, you're going to have to become 4 degrees Celsius.
Yeah.
Eventually, the water at the surface is going to be 4 degrees Celsius. Why? Because it's getting cooled down by the frigid air.
Yeah.
The moment that water at the surface becomes 4 degrees Celsius.
Becomes denser.
It becomes the densest it can be. What's it do next?
Freezes.
No, it's still liquid. It's 4 degrees Celsius. It's really dense.
Well,
What's it do?
I should think it would start forming crystals.
No, that's not going to happen until it's 0 degrees Celsius.
Oh.
You're a blob of 4-degree water at the surface of this pond, of this liquid pond. What are you going to do?
It's going to shrink.
Well, it's contracted. Yes, it has, and now it's dense.
Yes.
Now, after you have this dense blob of 4-degree water,
Yes.
what's it going to do? Float up into the air? No, it's
No.
going to stay in the pond.
Yeah.
At the surface of the pond? Meanwhile, it's 10 degrees down below
Well, down below, it's warmer.
because it hasn't been exposed to the,
That's
to the
right.
frigid air yet.
That's right.
Yeah.
So, down below will start to cool.
Not yet.
Well,
It's still away from the air.
I know, but as the water at the top of it gets colder,
Down to
and
4
denser.
degrees.
Yes.
Denser. At 4 degrees, you're telling me the water, that blob of water is most dense?
yes, it is.
What happens when you take something that's really dense and
It
you put it in
shrinks.
water? Does it float or does it sink?
It sinks.
It sinks? So you're telling me that blob of water at 4 degrees Celsius is not going to stay at the surface?
Well, if it goes down to the bottom, it's going to make the bottom colder too.
As it goes down to the bottom.
And then it's replaced by other stuff at the top.
Okay, water from the surface is going down to the bottom,
Yes,
right?
right.
What's the water down at the bottom going to do?
Shiver.
It's going to go up. Because now you have water that's 4 degrees at the bottom.
Right, because it's denser.
The densest water always sinks to the bottom.
And so it pushes the bottom one further up.
Yeah, it takes
But
the
then when
bottom
it pushes,
water.
it's
gets
almost
into-
like reverse boiling, actually.
It's you create these little currents, vertical currents.
Right.
So back up, we have frigid air,
Yeah.
and that frigid air cools a blob of water at the surface from 10 degrees to 7 to 6 to
Yeah.
5 to 4 degrees. It gets to 4 degrees, and before it gets any cooler,
Yeah,
it sinks.
it does.
It sinks to the bottom of the pond, displacing the water at the bottom of the pond, which rises to the surface. So now at the surface, you now have 10-degree water again. What happens to that 10-degree water now?
It begins to lose its heat.
It goes from 10, 9, 8, 7. Then it gets
Pretty
to
soon it gets to 4.
to 4. Then what
It goes
happens?
blum, 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 blum,
It
blum.
sinks, right?
Right.
But there's already 4-degree water beneath it.
I know it, so it begins
Right.
a layer of the 4-degree water, and
Yeah,
it keeps
yeah.
pushing more. It
And
hasn't
then- and then-
frozen yet, but it's dense.
So can
It's
you
still
see
water,
how
but it's
it
not
is
ice. It's dense.
that eventually the
Yes.
entire pond will become 4 degrees Celsius?
Yes, that's right.
And how it is that surface water it just cannot get any colder than 4 degrees Celsius until the entire pond itself is 4 degrees Celsius.
And then where is there for it to sink?
So eventually, because the water's densest at 4 degrees Celsius, it's always just going to sink to the bottom. And the warmer water underneath is going to rise to the surface to cool down. That
To 4 degrees
process is going to
Celsius.
go round and round and round
Yep.
until the entire pond is 4 degrees Celsius.
Oh,
And only
there's
then,
no place for it to go, so it has to stay there and get colder.
only then will the surface go from 4 degrees to 3 degrees.
Yeah, and from 3 degrees to 2 degrees, and from 2 degrees to the 0 degrees,
to
ice.
Ice.
Get your
Bam.
skates.
Yeah. Now, here's an interesting thing. If you have a lake that's really, really deep,
Yes. Oh,
it will never freeze over.
is that why it's still soft in the middle and you can go through?
Safer to skate by the edge of a pond than
Yeah, it
out
sure
in the
is.
middle, right?
Oh, I do remember that crack. Oh, my, yes.
So if you have a
It's-
really deep pond or lake,
Yeah.
you'll find it won't freeze over
That's right.
because you have to get that entire pond or lake
Yes.
to 4 degrees Celsius.
Yeah.
And winters just typically aren't long enough in temperate
Well,
regions.
sometimes it does. The pond is small enough, the whole thing does
Yeah.
freeze over.
Yep. So
And then you can go skating.
yeah, so that's how it is. Ponds will always freeze from the top down.
I think that's wonderful.
And that's good for aquatic life because that layer of
La-
ice that
the fish
forms,
can still swim.
it will insulate them from
Yes,
the colder
it does.
weather
It
above.
does. It does. It
Yeah.
does. That's wonderful.
Yeah, excellent. So we have some properties of water to talk about here in the next section.
Okay.
Surface tension is one of them. And what else do we have here? Capillary action. All right, surface tension and capillary action. So envision just some liquid water,
Yes.
and we're at the surface of that liquid water. And above that liquid water, you got air.
Right.
Now, consider yourself to be a water molecule on the surface. You look around you and underneath you, you've got water molecules pulling on you.
Yes.
But you look above you, and there are no water molecules.
No.
You've only got water molecules from the side and from underneath.
And you stick to the ones to the side and underneath, but you can't stick to what's above you.
Yeah. There's something different that's going on.
Okay.
So consider now you have a pin, and you want to poke the pin into the water.
Yeah.
As the pin goes into the water, it has to separate water molecules from each other in order to get to the underneath.
That's right, because it has to go through them.
It has to go through them. And consider the water molecules like all holding hands.
They are. They're playing their games.
And they're holding hands with the dipole-dipole attractions.
Yes.
And so for that pin to go into the water,
Ouch.
it has to poke through and actually break some water molecules apart from each other. And they don't want to do that.
You should not be able to do that. That's
so
not nice.
what happens is the surface of the water, because of all the attraction among the water molecules,
Yes.
behaves very much like a rubber sheet.
Oh,
And
really?
here's an activity you might have done. You can take a paper clip
Yeah.
and you can very carefully, gently lay it on top of some still water, and the paper clip will
Float.
not sink.
That's the same as floating.
Not really.
Oh, really?
Yeah, correct.
Why?
What it's doing is it's resting. Now, if you take a bowling ball and put it on a trampoline, would you say the bowling ball is floating on the trampoline?
Of course not.
No, the bowling ball is sitting on the trampoline, pushing it down a little
Yes.
bit, right?
And then it comes back
But
up
it's not
again.
floating on the
No,
trampoline.
no.
Well, the same thing here. That paper clip is not floating. It's actually on the surface of water, just as the bowling ball is on the trampoline.
Okay, right.
It's resting on the water.
Yeah.
But it has weight, and so it depresses the water downward a little bit.
Does the water mind?
It does. It bends down inward.
Yes.
But
and
it
it's just-
holds it up there.
because it's still holding hands underwater.
Yeah.
Yes, okay.
Yeah. If it were floating, it would be like a boat. It would be partially
would.
submerged. It's not
Yes, it
submerged.
would.
Yeah, it's not submerged at all.
Okay, I
It's
understand.
on the surface.
Right. I understand.
Yeah.
Wait a minute. Why doesn't it sink?
Because all the attractions of water molecules for each other,
Yeah.
that makes it like a barrier, a rubber barrier. That's difficult, relatively speaking, to penetrate. If you push down on that paper clip, yeah, it'll sink for
Right,
sure.
right.
But if you lay it very carefully on the water, you can get it to rest on top of the water. And it's an activity you should all try at home if you haven't already. And that's how water bugs will skim across
skate
the
across
surface.
it. Oh, I've seen
yeah,
them. We call them skating.
Yeah, skating bugs.
But it's not ice, it's water.
yeah.
But they're very light. Well,
Yeah.
wait a minute. If never mind, keep going.
All right, next thing we're going to look at here is capillary action.
Yeah.
And it results from an interplay of what we call adhesive and cohesive forces.
Really? What's the difference between adhesive and cohesive?
Well, adhesive means it's a dipole-dipole attraction
Yes.
between two different materials.
Yes.
Cohesive means it's a dipole-dipole attraction within a material. So you understand with
Okay.
liquid water,
Okay.
you have water molecules, love water molecules.
Yes.
Those we would classify as cohesive forces between those water molecules.
Mm-hmm.
Now, water is also attracted to glass, which is also
Why?
polar. It's made of silicon dioxide, which is a polar material. So when we talk about adhesive force,
Mm-hmm.
we're talking about an attraction between two different materials. And a good
Mm-hmm.
example would be between water and glass.
Mm-hmm.
So water will adhere to glass.
It does.
Water will cohere to itself. Consider water in a test tube. If you look very carefully from the side,
Yeah.
you'll see the water is actually creeping up the edges.
That is totally weird.
It's called, you know that term?
Meniscus.
Meniscus, yeah. For the water adhering to the sides of the glass, what happens is it rises on the edges. And it's because of the adhesion between the water and the glass.
But wait a minute. how does it know? Why doesn't it just adhere where the water is poured into it? Why does it climb up it? So why does it go higher? That's what's so weird.
Oh, I get you. Yeah, it actually creeps up the edge.
Why? How can it do that? You're silent. Well, maybe it's just it likes it so much that it wants more.
I like that.
And so therefore, it's just sort of like, my word, this glass tastes really wonderful.
Because the question really is, why doesn't it keep rising to the top?
And why doesn't it? If it wants it, well, I think it runs out of steam.
No, something g starts with g, rhymes with avity.
Gravity.
Gravity's pulling it down.
No kidding.
Yeah.
Well, how come it overcame gravity? That makes it pretty strong, doesn't it?
Well, they're strong enough to create what we call a meniscus. So the water will rise up the edge
is
of
meniscus,
the glass.
Is the edge the meniscus?
The curvature of the water that you see, that's called the meniscus.
In other words, it is the edge, right?
Yeah.
Okay.
On the surface.
That explains it.
Yeah. There's the adhesive forces between the water and the glass, but there's also gravity pulling it downward. And there's a third force, it's a cohesive force between water and water. And what happens is, if your capillary is narrow enough,
yes,
the water will want to form a ball.
Really?
Yeah, in the middle. It kind of balls up.
Really?
And yeah, that'll actually help it to rise also. Put it this way. You have the water molecules creeping up the edge, right?
I guess so.
Those water molecules that have just creeped up the edge are going to say to the other water molecules, hey, everybody, come on up here.
The water's fine.
And they do. If your capillary is narrow enough,
they can keep right on going.
They'll keep on going. And the cohesive forces between the water actually help that matter.
But the cohesive then overcome the gravity. Because if the gravity's pulling down, it's pulling down all the time. It's not pulling down sometimes.
Yes. So, but only when you have a narrow capillary will it be able to overcome the gravity, because there's not that much water. If you have a very wide bore capillary, then you're talking about trying to elevate too much water, and the gravity, with not enough glass surface around it.
That's true.
So the gravity will win over, and so it's not going to rise.
It makes sense to me.
So capillary action is this interplay between adhesive, cohesive forces, which can be counteracted by gravity.
I want you to say one more time what a cohesive force is.
Cohesive forces are the interactions within the same substance. So you have a water molecule and you have a water molecule. How would we categorize that interaction between those two water molecules?
Cohesive.
We would say they are cohesive forces.
Of course we would, right.
It's still dipole-dipole.
Okay.
Whether it's between the water and the water or the water and the glass. It's all dipole-dipole. But we categorize, when it's two different materials, that as adhesive. When it's one type of material,
it's cohesive.
We call that cohesive. And the interplay between the adhesive and cohesive forces can cause the water to move through tiny capillaries.
Yeah.
They have to be tiny, because if they're any larger, gravity takes over.
That's right. It would be overwhelming.
And this explains how water can rise from the water table underground to the roots of a tree. It's actually capillary action that allows the water to creep upward to the roots.
Yeah.
The tree isn't actively sucking up the water from underground. It's just a natural capillary action that brings the water upward. It draws the water upward.
Because there are little teeny
little capillaries, pathways through the soil, which is why a really compact soil, it's not going to happen. So the quality of the soil is important. A good quality soil is a soil that has those little capillaries through it that allows water to permeate throughout so that it can get to the roots.
Right.
All right, ready for the next section?
Oh, yeah, I know, but I'm just seeing why it's so hard to plant things in the middle of clay, which is what you do in Texas. All right, go on.
Well, actually, I'm thinking we're at a good stopping point. We've made it through the first half of this chapter on the remarkable properties of water. Mom, you're an awesome co-host.
Yeah.
Might you be willing and able to stick around for the second half?
I think this is wonderful.
Awesome. All right, we're going to do this. Appreciate it. Hey, listeners, thanks for tuning in. In the next episode, we'll be exploring how water transforms into the gaseous phase, as well as how water behaves very much like a heat sponge, which has all sorts of environmental implications that we'll talk about. So, till next time, good chemistry to you.
Let's go make a cup of tea.
Our theme music by Zach Jeffrey. Musical flourishes by George Friedrich Handel. Selections from his Water Music Suite in F major. Our thanks to Marjorie Hewitt-Suhaki, Emeritus Professor and Dean of the Claremont School of Theology. Production assistance from Greg Simmons and CPRO Music. For show notes and more, please visit conceptualscience.com. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry. Good chemistry to you.